Scientists have been making a lot of predictions in the past year. But here's a secret. One of the methods they use is so simple that anybody can try it at home. Today, it's your chance to be an epidemiologist. Modeling a disease may seem difficult because there are so many variables involved, from human behavior to the biology of the pathogen, to preventative measures, and even an element of randomness. Luckily, the SIR model can simplify things.
In SIR, we divide the total population into three groups: the ones who are susceptible to the disease, the ones who are infectious, and the ones who have recovered. S, I, and R are kind of like train stations. When a person is infected, they hop on a train from S to I, and when they recover, they go from I to R. The amount of people on each of these trains tells us the rates of infection and recovery.
Knowing these rates can tell us whether an infection will spread fast or whether it will burn itself out.
Let's start with the rate of new infections. This depends on the probability that an infectious and a susceptible person meet. To top it off, we add a constant that accounts for other factors such as hygiene and how often people in our population meet each other.
Because this constant covers so many things, it's hard to calculate it directly. Instead, we just estimate it to fit data that we already have.
Now for the rate of recovery. This depends only on I, because in our model, you can only recover after being infected. We also add another constant to account for the average time taken to recover. Each train removes people from one group and adds them to another. Putting all this together, we get a system of differential equations, which tell us how each of our groups change in time. We can solve these equations to get formulas that will tell us the exact number of people in any group at any time. But there's a catch.
These equations are not easy to solve.
So we have to use a computer. First, we provided with initial data on the SIR populations and our two constants. Then, we make it calculate the changes in each group for a particular time step, like a day. Finally, it updates the values for each group and repeats this process.
When scientists do this, they often add extra compartments or links to better simulate the real world.
For example, a quarantine group to control the spread of the disease, or a direct link from S to R to represent vaccinations.
Sadly, the real world is far more complex, and no model can give us accurate dates or values. What they can give us is an idea of what the future holds, allowing people and governments to prepare themselves.